Hi, in this video, we're going to take a look at chapter 2 of the textbook on ggplot. All right, so the goal of this video, the goal of this chapter is to go from 0 to capable in as short of time as possible. All right, so think about this video as learning Mary Had a Little Lamb when you're learning music. All right, learning this is not going to make you an expert, but you're able to do something coming right out the gate. And that's what I hope that you get out of this video. So, all right, so we're going to be taking a look at the online textbook on ggplot2 by Hadley and these individuals. I appreciate their work. Here is the textbook's website, and here's where you can get the R Markdown file that I use to generate this. Now, things are modified because I'm creating lecture notes. This is a textbook writing, but very good. So you'll see some differences if you scrutinize it closely. Um, these guys, they know what they're talking about. All right, so this code chunk is how I like to start any project that I work on. So not going to really worry about that. So now let's get to first steps, introduction. All right, ggplot allows you to make complex plots with just a few lines of code because it's based on a rich underlying theory, the grammar of graphics. There are three components to every plot: the data, the aesthetics, and the geoms. The aesthetics defines how the data is mapped to the image, and it's a mathematically proper mapping, by the way. Now, you can add additional variables to a plot using aesthetics. You can display additional categorical variables using subplots by faceting. Every type of plot has a geom, so there's a geometric aspect. We can modify our axes, and with a plot, you can display it, save it as an image, as a PNG, JPEG, something like that. Save it as an object in R, and you can extract the under the hood information of the plot. All right, so the textbook uses the fuel economy data, which is called MPG, miles per gallon, from the U.S. Environmental Protection Agency. Here is where the textbook cites the data. And so we've got the manufacturer of the car, the model of the car, the displacement of the engine, the year of the model that's in the data set for that row, number of cylinders, the transmission, the drivetrain, which will be front-wheel drive, rear-wheel drive, and four-wheel drive, city miles per gallon, highway miles per gallon, then FL, and class. I can't remember what FL is, and it's not listed here. Okay. All right, so some very interesting questions just naturally arise when I have this data. So if I have the data, I can answer certain questions, such as how are engine size and fuel economy related? Do certain manufacturers care more about fuel economy than others? Has fuel economy improved in the 10 years of the data set? All right, so the key components of a plot are, number one, the data. Two, the aesthetic mapping between the variables in the data and the visual properties of the image. And at least one layer which describes how to render each observation. Layers are usually created with a geom function. Okay, and so when I say geom, here is the first example, which will be geom point. So check out this code. All right, first thing I want to point out actually is I recommend that when you write your code, notice that I have the parameter word data right there. I have mapping there. I have explicitly X and explicitly Y. If somebody was not familiar with ggplot and they looked at this, it would be easier for them to figure out that displacement and highway are the Cartesian coordinates and the data is coming from MPG. Now, Maybe they'll have trouble with mapping. Maybe they'll have trouble with geom and ggplot and what does it do. But if you tell them that this is a plotting function, they immediately know that MPG is the data object, and they immediately know what the X and Y coordinates are right off the bat. So I recommend you write your code like this. Notice that I'm very disciplined in using the names of my parameters whenever I can. Okay, now in this video, I'm going to go away from that. And the reason for that is that I'm going to have a simple, like, routine aspect of the plot, but then I'm going to tack on geoms. I'm going to modify things. I want you to be able to see the variations. So I want for you to be easier for you to like scan through and see this, with these being pretty simple plots that are coming up. At work, professionally, this is how I write my code. But for the purpose of instruction in this video, I'm going to break my own convention. All right, so what do we have here? We've got ggplot as a function with two slots being used. We have the data slot and the mapping slot. The data is the miles per gallons data set. And then mapping, you'll notice that this is the output of the AES function for the X and Y Cartesian coordinates. So this defines the aesthetic mapping from the variables to the visual properties of the image we're about to look at. Now, the geometry of the image is coming from geom point. This is indicating I want a scatter plot using these X and Y coordinates. All right, so let's go ahead and take a look. All right, so one thing that I can see, I've got displacement along the x-axis, the horizontal axis. I have highway miles per gallon along the vertical axis, the y-axis. And when I look at this, to my eyes, it looks like there is a negative correlation between displacement and highway, that as displacement increases, to my eyes, highway miles per gallon decreases as we go with like a negative slope along here. So the code produced a scatter plot using the data of miles per gallon, aesthetics mapping, engine size was mapped to the X position, fuel economy was mapped to the Y position, and then a geometry layer of the points. So pay attention to the structure of the function call. All right, the data and the aesthetics mapping was inside ggplot, and a plus sign was indicated that we were adding on a layer. So the data and the aesthetic are inside ggplot, and then I use a plus symbol to add a geometric layer to the plot. This is an important pattern, and as you learn more about ggplot, you'll construct increasingly sophisticated plots by adding one or more types of components. Almost every plot maps a variable to X and Y. So naming these aesthetics is tedious. So the first two unnamed arguments of AES are X and Y. Okay, so this code here is going to produce this exact same plot as I had above, but you'll notice I didn't name anything in here. So I've got the data slot is the first slot within ggplot. The mapping slot is the second slot in ggplot. And then inside the aesthetics, the mapping, X is the first position, Y is the second. And so when you look at ggplot code, remember the first slot is miles per gallon, the second slot is mapping. Within the mapping, it's X and Y, and then the other ones follow. Now, I recommend that you use your parameter names every single time that you can, but most people don't, honestly. I think it would be better if they did, but they're free to do what they do. It's their project, they're professionals. They can handle it their own way. So, we just need to be familiar with the first few, honestly. All right, and if I take a look at this plot, I'm going to get exactly the same plot, even though I have that slight modification. So remember that the first two arguments of AES are X and Y. And it's normal convention to put a new command on a new line. And so, a new command on a new line is recommended to do this by the textbook authors and myself in your own code. So it's easy to scan a plot specification, see exactly what's there. This particular plot shows a strong correlation. As the engine size gets bigger, the fuel economy gets worse. Also, there's some interesting outliers. Some cars with large engines get higher economy than average. So if I'm looking over here, look at these guys over here. Huh. It would be interesting to know which vehicles those are. Well, we'll go and we'll find a way to figure that out, to plot it. All right, now let's talk about the color, size, shape, and other aesthetic attributes. To add additional variables to a plot, we can use other aesthetics like color, shape, and size. Now, something you'll notice if you are an American, that U in there looks really weird to us. ggplot accepts the American and the British spellings. So just be ready for that as you work through things. Now, these work in the same way as X and Y aesthetics, and they're added into the call of AES in these code clips right here. So here I've got the same X and Y that we looked at a moment ago, but now in this one, we're saying that class is mapped to color. Drivetrain is mapped to shape, and then cylinders is mapped to size. Now, something that's nice is that ggplot2 takes care of the details of converting the data into aesthetics. So, for example, for the drivetrain, front wheel drive, rear wheel drive, and four-wheel drive figures out the shape immediately for us. I don't have to do anything about it. I don't have to figure it out. While also class of the vehicle is mapped to the color immediately, and furthermore, ggplot takes care of the scale of the plot for us. There is one scale for each aesthetic mapping within a plot. Now, one thing that's also nice is that ggplot's scale system is also responsible for creating a guide, an access, or legend that allows you to read the plot. So this helps us convert aesthetic back to actual data values. To learn more about these underlying variables in the previous scatter plot, we could map the class variable to the color. All right, so here, I'm going to go through and I'm going to just tack on, and this is in the version that I had of the original, I'm going to add class of the vehicle, and that's going to get mapped to color. That's the only thing that's changing in this plot. Everything else is the same. I'm going to have the same X and Y coordinates as before. I'm going to have a scatter plot. I have the same data, but now the dots are going to be different colors to indicate the class. All right, and so now I can look through, and something I notice is like those outliers that were pointed out before that had larger displacement are two-seaters. Ah, okay, that's kind of interesting. And so we've got a midsize also up over here. So these are probably sports cars, honestly. So these are probably this midsize one is actually probably a luxury car with a powerful engine, while these guys are sports cars since they're two-seaters and they have a lot of displacement in their engine. But overall, I can see that negative correlation going on. All right, so by adding the color, this gives each point a unique color corresponding to its class. The legend allows us to read data values from color, showing us that the group of cars with unusually high fuel economy for the engine size are two-seaters, cars with big engines but lightweight bodies. If you want to set an aesthetic to a fixed value without scaling it, do so in the individual layer outside of the aesthetics function. So compare these two plots. All right, so I've got that base aspect that I had before. So I've got ggplot, I've got data, I have the mapping, I have geom point, but now I've got aesthetic on the inside of geom point. So something about this is that we can put the aesthetic actually inside ggplot, inside our geoms, and actually use a plus sign to add it on. We have a lot of flexibility when we're doing ggplot. All right, so what I want to do, I want to map blue to a color. Okay, so all right, I'm feeling good. I'm excited. I'm learning ggplot. I'm new to this. And then I look at my plot and I say, huh, that's not blue. That's red. What's going on? It says blue is red. What's happening? All right, so what's going on is that if it's inside the aesthetic, if it's inside AES, it's looking for this to be a variable in your data sets. And since it's not there at all, it's just going with a constant value. All right, so that's why this failed. All right, so let's go ahead and change this up now. Notice that I have color blue, but I don't have the aesthetic. Up here, I've got aesthetic around it. Now I don't. Look what happens. Boom, check that out. Now I've got blue dots. All right, so if I want some constant value across all of the geometric objects, I don't want the command inside AES. If I want a data column to impact the visualization, I want it inside AES. Now, there's a couple of other ways I can go about this. So let's say that I really, 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 really want to have color inside AES. I can use the identity function for this and I can force it along the way. But, here I have an unnecessary aesthetic and an unnecessary identity call. So this is more complicated, but this is a way for me to make it happen if I want that option. And now I don't need the identity function on this. If I remove the identity function, we would have our first blue scatter plot, but it works out. It's fine. I could have identity. I could not. It'll work out beautifully. Everything's good. It's just that whatever I put in this position has to make sense for this. So like if I had size, I couldn't put blue. That wouldn't make sense. For color, I couldn't put 2. That wouldn't make sense. I have to put in something that ggplot can interpret for the mapping. All right, in the second plot, the value blue is scaled to, or sorry, this one, in the first plot, the value blue is scaled to a pinkish color and a legend is added. In the second plot and the third and fourth, the plots are given our color blue. All right. The first 2 plots are from the textbook. The third and fourth, I added those on myself. So why third and fourth are not mentioned? All right, so constants inside the mapping and the role of the identity function. Anything placed inside AES, which is doing the mathematical mapping, is treated as data to be scaled, data to be mathematically mapped. This includes literal constants inside AES. So, for example, putting color equals blue. All right, so if I run this, ggplot2 will interpret blue as a categorical data value, generate a scale, and most of the time we'll add a legend, depending on the geom. The cleanest way to set a constant visual property is to set it outside of AES, inside the geom call. Like for example, for geom point, I can have the constant for the color declared outside of the mapping. Boom. However, there are situations where you do want to place a constant inside AES. For example, well, if I'm writing functions that programmatically build mappings, or when you want the value treated as is, like explicitly within the mapping context. In those cases, use the identity function to indicate that it should be taken literally. And so this will inhibit the scaling of the values. Now, another thing to talk about, when I have a lot of data points, when I have a large data set, we can have overplotting. Overplotting is when I've got data in the visualization that stacks on top of each other, and I can't tell that I have multiple data points on there. So imagine I have the exact same data point 1 million times. Now it's the same data point every single time, and I do my visualization, I'm gonna have 1 million stacked on top of each other, but visually I only see one because it's one location. All right, that is overplotting. And so overplotting can make dense regions look like solid blobs, or sparse regions can, like, practically disappear. One of the simplest fixes is to reduce the point opacity using the alpha aesthetic or parameter. Alpha ranges from 0, full transparency, to 1, fully oblique. So in that situation that I've got points stacking on top of each other, think in terms of how many points need to stack before the region looks opaque. So values like 1/10, 1/20, 1/100 makes it easier to interpret what the alpha value will be. If I put in 1/10, there I'm saying when I stack 10, I want a solid opaque dot. And when I have 1, I want to be very transparent, and I want a gradient in between there. And so if I have 1/100, when I only have one dot and there's nothing stacked on top of each other, I'm gonna barely be able to see that dot. But if I have 95 dots stacked on top of each other, it's gonna be very, very dark, but not as dark as 100 of them. And so this fraction scheme is more intuitive than decimals because the denominator is loosely scored to how many overlaps it takes to saturate the color. This makes it easier to tune alpha quickly while exploring dense scatter plots. Now, different types of aesthetic attributes work better with different types of variables. For example, color and shape work well with categorical variables, while size works well for continuous variables. The amount of data also makes a difference. If there's a lot of data, it can be hard to distinguish between different groups. An alternative solution that's also used is faceting, creating subplots. When using aesthetics in a plot, remember, less is more. Less is more, less is more. It's more important to convey the most fundamental, most important information than it is to convey all information. I've made this mistake. And so if you try to throw in every variable that I've got into the plot, it's going to make a visualization that people are not going to be able to interpret. All right, so it's difficult to see the simultaneous relationships among colors, size, and shape simultaneously. So exercise restraint when using aesthetics. Instead of trying to make one very complex plot that shows everything at once, see if you can create a series of simple plots that tells a story, leading the reader from ignorance to knowledge. All right, so here, this is going to be a bad plot. This is a plot that I would not show at work. Here's what I'm doing. I have X and Y, all right, okay. But now I'm gonna have color, shape, and size. I've got 3 aesthetics going on. Now, when I do this, notice that there's just a lot going on. There's a lot to figure out. I've got, this purple triangle here, that purple triangle, like how are these different? How are these the same? I don't understand. There's a lot of things going on here. And, in this presentation, when I use size like this, it's likely that I would just completely ignore the small displacement, or sorry, not the small cylinder vehicles. Now, the information is correct. Everything about this plot is right. Everything is meaningful. It's mathematically correct. But for a human being to figure out what's going on, this is going to be difficult. So I don't recommend using this. Faceting. So this is building subplots. Another technique for displaying additional categorical variables on a plot is faceting. Faceting creates tables of graphics by splitting the data into subsets and displaying the same graph for each subset. All right, there are 2 types of faceting, grid and wrapped. Almost everything I do for work is wrapped, by the way. Grid is really slick when I need to get a lot of data onto one plot, but wrapped is usually the one that I use. So wrapped, and this is coming from the authors, I agree with it. Wrapped is the most useful, so it's the one that we're going to use here. To facet a plot, you simply add a faceting specification within facet wrap, which takes the name of the variable preceded by the tilde. Okay, so I'm going to take the X and Y coordinates I have before. I'm going to do the geom I've done. Now for facet wrap, I'm going to split it by class. I want to see a subplot for each class of vehicle. All right, so some things to notice. Notice that all plots have the same X and Y scale. So what could have happened if I would have specified it is that the compact plot could have had a narrower horizontal coordinate and actually Y coordinate also. But instead, it set up that all 7 plots have the same X and Y scale, so it's easier for me to compare. Sometimes I'm going to want that, sometimes I'm not. But we can go through the two-seaters. I can see her to the right, compacts are to the left, midsize has a bit of a range, subcompact has a bit of a range, pickup has a range, and you notice that it's lower. That's kind of interesting. Minivans have, a cluster going on here. SUVs has a bit of a range horizontally. Okay. So now plot geom, by substituting geom point for a different geom function, we'll get different types of plot. So geom smooth is going to smooth the data and display, by default, it's going to display the standard error. And so typically this will be a lowest or a generalized additive model will be added to the plot for us to see like what is that central tendency aspect. Geom box plot will produce box and whisker plot to summarize the distribution of a set of points. Geom histogram and geom frequency plot show the distribution of continuous variables. Geom bar shows the distribution of categorical data. Geom path and geom line draw lines between data points. A line plot is constructed to produce lines that travel from left to right, while path can go in any direction. Lines are typically used to explore how things change over time. All right, so now let's talk about adding a smoother to a plot. All right, so we're talking about geom smooth. If I have a scatter plot with a lot of noise or a lot of points, it can be hard to see the dominant pattern. What I want to do, I'm going to put down the scatter plot. Then on top of that, I'm going to put a function that smooths out the pattern and makes it so I can see what's going on. All right, so I've got 4 different options. I've got lowest, which will do local regression and is a good choice for smaller data set. GAM will do a generalized additive model, which is good for larger data sets. And by the way, if it's a large data set, ggplot will automatically use GAM. If it's a smaller data set, it will automatically use lowest. You don't need to tell it. But if you wanted to switch, you could manually. Now, we could also get a linear model, and we could do a robust linear model for it. So let's go ahead and do this. I'm going to add geom smooth. So this is the code that I had before. I'm going to add on geom smooth. Now here, it's a small data set. By default, since I did not specify the method, it's going to give me a lowest curve. Boom, look at that. So now I can see what is the conditional, central tendency of highway miles per gallon, by displacement. Also, we get a standard error estimate of the expected value by default. I can remove that using SE equals false, by the way. This overlays the scatter plot with a smooth curve, including an assessment of uncertainty in the form of point-wise confidence intervals shown in gray. Now, all right, so how this works is that first thing that happens is ggplot is set up. It figures out the data, figures out the mapping of the data. First thing that happens next is for the points to be plotted down, and then geom smooth comes out after that. And so whatever is first in the code is lowest in the plot. So if I'm putting on multiple geoms, they stack on top of each other. Notice that the blue is on top of the black dots. That's because geom smooth was stacked on top of geom point. If we don't want that confidence interval, we can just set SE equals false within geom smooth. An important argument to geom smooth is the method, which allows us to choose which types of model we'll use for fitting the smooth curve. So, if I want a linear model, if I'm in a linear regression project, I'm going to set the method to LM. Method equals lowest is the default for small n. I think small is defined as 1,000 or less, and uses smooth local regression. The wiggliness of the line is controlled by the span parameter, which ranges from 0, which is very, very wiggly, to 1, not so wiggly. Okay, so let's go ahead and decrease the span to 0.2. Now you see that's very, very wiggly. I honestly wouldn't accept this model for this purpose. Could put span equals 1. All right, that doesn't look too shabby at all. Lowest does not work well for large data sets. So an alternative smoothing algorithm is used when n is greater than 1,000. Method generalized additive model provided by the MGCV package. So we'll have to load. So this says you have to load it. You have to install it. Notice that I did not use library MGCV. I just commented that out. At least on my machine, didn't have to do it. It automatically figured it out for me. And then we need to use a formula like y depends on s of x, or y depends on s of x, bs equals cs for large data. This is what ggplot uses when there's more than 1,000 data points. All right, so I'm going to go ahead and say, hey, I want a generalized additive model. And here's the formula. This is the spanning aspect. And so here, you notice that there's a little bit of a bump here, a little bit of wiggle that wasn't in this part. Now, which one's correct? It's up to you. You're the data scientist. You have to make that subjective decision. Now, if I want a linear model, I'm going to put method equals LM, which if I'm doing a linear regression project, definitely the plot I'm going to use. And so here I've got that. I've got the line of best fit. Now, also, maybe I need robust linear regression. Maybe I know that the assumptions that are needed for standard, line of best fit linear regression doesn't hold. So let's go ahead and use robust linear model from the mass package. And so boom, I've got that. Method is equal to RLM. And for this one, it looks pretty similar to what we have in just regular old LM. All right, now let's talk about box plot and jittered points. When a set of data includes a categorical variable and one or more continuous variables, you will probably be interested to know how the values of the continuous variables vary across the levels of the categorical variable. Say we're interested in seeing how fuel economy varies within cars that have the same kind of drivetrain. All right, so what I want to know is, given the drivetrain, what is the distribution of the fuel economy? Okay, so I'm going to set X to the drivetrain. I'm going to set Y to the highway miles per gallon, and then I'm going to have geom points plotted. Okay, and so this is a mathematically correct plot. I've got four-wheel drive, front-wheel drive, rear-wheel drive, but honestly, looking at this, I know because I already looked at the rest of the video, I've got dots that are stacking on top of each other, and I have no idea which dots are stacked on top. This isn't a very good plot when I have overplotting. Okay, so because there are few unique values, of drivetrain and highway miles per gallon, there's a lot of overplotting here. Many points are plotted in the same location, and it's difficult to see the distribution. All right, this can be a problem when I have repeated values or I have a very large data set and there's just so many of them that they end up just stacking just because there just isn't enough variation in the data. All right, geom jitter adds a little bit of random noise to the data, which changes the values, but moves the data points away from each other so it's easier for me to see the pattern. Geom box plot does a 5-number summary to summarize the shape of the distribution with summary statistics. Geom violin shows the density of the distribution. And so this highlights the areas where more points are found. All right, so let's go ahead and just take a look at geom points. So I'm just repeating the code I had before. And now I'm going to, instead of geom point, I'm going to do geom jitter. So check out, so in your mind, hold on to what these guys look like, scroll down. Now, hey, whoa, things look very, very different. What has happened is that the X and Y coordinates were wiggled just a little bit, they were jittered. And so now I can see how many dots are in each of these 3 groups. We can see that rear-wheel drive is less frequent than front-wheel drive and 4-wheel drive. Now let's use geom box plot. Geom box plots, I can see the median, the interquartile range, and then minimum or maximum, eliminating outliers. And so this is the minimum of the values that are not considered outliers by the calculation used here. This is the maximum that's not considered an outlier in the calculation used here. And then I've got the minimum and maximum. And these guys are outliers because they're so far by a metric. We'll talk about this later. And now here I can look at the same data, but now I have geom violin. What is happening here is that we're doing the empirical density estimate, probability distribution estimate, and which normally the plot would be like this. We're going to take it, we're going to put it on its side, and then we're going to reflect it. And so this way I can see, where do I have the clump of points, right? So notice that I have kind of like a clump here and a clump here. And when I scroll down, I see that clump here in the wider aspect of the violin plots. Each method has its strengths and weaknesses. My experience is that everyone who's not a professional statistician hates box plots. Do not use box plots. Box plots summarize the bulk of the distribution with only 5 numbers. It's a 5-number summary. Jittered plots show every point, but only work with relatively small data sets. Overplotting will be an issue if I have a large data set. And violin plots give the richest display, but they rely on calculation of density estimates, which can be hard to interpret. Also, I feel like stakeholders are not going to appreciate violin plots, and they're not going to appreciate box plots. More likely, jittered plots, when I show a jitter plot at work and somebody does not have a math background, I can say, you know what, each dot represents a subject, but I wiggled it around so that they don't overlap on top of each other. For jittered points, geom jitter offers the same control over aesthetics, size, color, and shape. For geom box plot and geom violin, we can control the color of the lines, that is the black lines, and the fill, which was the white portion. So the fill is the white, and the color is black on this one. The fill is the white, and the color is the black, just so you know what's happening. So if I set color equals red, the white part's going to stay, and everything that's black is going to be red. All right, now histograms and frequency polygons. Histograms and frequency polygons show the distribution of a single numeric variable. They provide more information about the distribution in a single group than box plots do, at the expense of needing more space. All right, so let's look at the histogram. This is geom histogram. after I'm just putting highway to the X coordinate and nothing else in there. And so here, this is the histogram. We can also do a frequency polygon here. I personally do not like frequency polygons because it makes it look like a time series. So my personal bias. Both histograms and frequency plots work in the same way. They bin the data, then count the number of data in each bin. The only difference in the display is that histograms use bars and frequency polygons use lines. You can control the width of the bins using the bin width argument. Now, if I want even more control over it, let's say I don't want evenly spaced bins, I can use the breaks argument. It's very important to experiment with bin width. And in fact, ggplot has a default warning that says, hey, check this, make sure that this looks right, try something else. The default just splits your data into 30 bins, which is unlikely to be the best choice. You should always try many bin widths, and you may find you need multiple bin widths to find the full story of your data. All right, my opinion is that you should usually use histograms to show univariate distribution. Frequency polygons can be mistaken for time series plots. Frequency plots work best when I've got unimodal distributions, and frequency plots can be better for comparing distributions with different subpopulations. So let's say that I want to compare either univariate data, like different columns, or the same variable across different subpopulations. Things can get crowded. Sometimes the frequency plots would be a better choice, but my opinion, overall, most of the time, I will go with a histogram. So let's go ahead and look at a histogram where I put bin width equal to 5. And so now we can see that, to me, this represents the distribution of the data better than the default settings. Now, if I put it at 2.5, now it's getting a little bit too nuanced to be right. Bin width equals 1. I think that this is too nuanced for the right conclusions, honestly. Now we can do exactly the same thing, but now I'm using frequency polygon instead of histogram. And so here's the plots, and these heights are exactly the same as the bars that I have here with a corresponding argument. Let's see, this is bin width 5. All right, so when bin width 5, these heights and x and y coordinates of each of these bars on the center is the same as the points that we have to make up the line right here. When we go to 2.5, we can see it looks jagged now, and then make it even narrower and it looks even worse. An alternative to frequency polygons is the density plot geom density. A little care is required if you're using density plots. Compared to frequency polygons, they are harder to interpret since the underlying computations are more complicated. They also make the assumption that are not true for all data, namely that the underlying distribution is continuous, unbounded, and smooth. To compare the distributions of different subgroups, you can map categorical variables to either geom histogram or geom frequency polygon. It's easier to compare distributions using frequency polygons because the underlying perceptual task is the same. What ends up happening, oh, actually, here's a good example. So notice that I've got drivetrain determines the color, and I've got the frequency polygon, and I can compare the 3 drivetrain groups very quickly. Now, this is going off of counts, not off of density estimates. The distributions here do not scale to an area of 1. Now, they could be rescaled, but these are not probability density estimates. Now, another way I could do, if you don't like this, and this is an all right way to compare frequency, I could also do 3 different histograms where I do faceting by the drivetrain. And so now I can look at the counts in this manner also. I prefer this version, but you do what works best for your project. Bar charts. The discrete analog of the histogram is the bar chart, geom bar. Okay, I actually use geom call all the time. And when I'm trying to show a distribution of continuous data, I actually will use the cut function to bend the data, and then I'll use geom call to go ahead and actually make the visualization. Geom bar is going to do the counting for me, and it does a lot of like slick things, but I recommend doing a little bit extra manual work and using geom call. But this is geom bar is an excellent function. Okay, so here I've got manufacturer. I want to know the counts of each manufacturer. I'm putting in the raw data. So then boom, I get the counts of each of these. So I can see that in the data set, Dodge is the most frequent, then followed by Toyota. Now you'll notice that I've got overplotting on the labels. They can overlap. Okay, there's ways we can handle that and deal with that. We're not going to talk about that in this video because we're trying to keep things simple. So I gave the original data as is. It went down the manufacturer column. It created a table of numbers, and then it visualized that table of numbers for me by counting. Bar charts can be confusing because there are two rather different plots that are commonly called bar plots. All right, so geom bar in ggplot, geom bar takes the data, does the counting for you. So this expects unsummarized data, and each observation contributes to 1 unit in the height of the bar. Each row of the data corresponds to 1 unit in the height of the bar. Now, geom call, so let's say that I went through and had the counts myself already. I did the counting, and I want to do a visualization. Geom bar isn't going to work. If I already have the counts, I need to use geom call. So let's go ahead and give an example. I'm going to take the miles per gallon data set. I'm going to group by the manufacturer. Then I'm going to count the number of times that each manufacturer comes up. And so now I have a count of the frequency of each manufacturer. Now, if I have my data in this format, this is a pre-summarized data set, I want to use geom call to display this. I don't want geom bar. I recommend that this is how you go because what inevitably happens at work, you give a visualization, you give a presentation, everybody's happy, they're pumped up and excited, and they'll say, please share the data that you use to make that visualization. If I use geom bar, I don't have it right. So something that I do professionally is that every time I do a bar plot, I create this data frame, this table of data, then I save it. Actually, I'll save it as one sheet of an Excel file. And then I keep that in my back pocket. I create the visualization. I show the visualization. Then when someone goes, hey, could you share that data with me? Boom, I've got it immediately. Why is this important? Sometimes your data changes. All right, I've had that happen. Your data gets updated. I've had the experience where the data architect actually takes down the table that you use for the visualization, and now all of a sudden I need that data to reproduce it, but now they just took it down. I'm expected to deliver very quickly because it's a high-level person in my organization. That's a problem. So I always save my summarized data. Every time I do a bar plot, I save the data that I use to build it. Each visualization gets its own sheet within an Excel file, and then boom, they ask for it. I can give it to them, easy peasy, lemon squeezy, nice and quick. And you'll notice that we get exactly the same visualization that we do with geom bar. Now, geom call has that extra layer of getting the summarized data, but this just gives me more control. We need to have both geom bar and geom call in our tool belt. To display this sort of data, I would need to tell geom bar to not run the default stat, which bins and counts the data. If the plot is crowded, consider using geom point. And in that case, what it'll do, it'll put a dot at the height, but that tends to imply that we're doing a scatter plot, which can confuse your stakeholders. I find that if I've got categorical along the x-axis, I want a bar, not a dot. But when things get really, really crowded, we could go through and use points instead of bars. Now, let's say that I wanted to use geom bar instead of geom call. I could use stat equals identity, specify the y coordinate, like I did with geom call, and then boom, I get exactly the same visualization. Here is it with geom call like that. Now, when things get very, very crowded, instead of a bar plot, I could use dots. So Audi's count is here, Chevy's count is here, Dodge's count is here, and I can read this, but people will want to visually play connect the dots. So I avoid doing this. If I really needed something like this, I would honestly switch the X and Y coordinates, and then I would label each of the dots by their manufacturer. And that would probably, solve the problem. All right, so advice on bar plots. All right, so my experience is that in real life, actual data science that people pay you to do is that bar plots are the workhorse of data visualization. Unfortunately, data science education, statistics education really doesn't emphasize bar plots not. I do, compared to my education, I do bar plots way more than I expected. Bar plots display categorical data and are mathematically simple. All right, so categorical data is the lowest level of data, and they're mathematically simple. So you know what? People in universities don't really find them interesting. But you know what? Applied data science is filled with categorical data. We have a lot of categorical data. It's how a lot of your stakeholders are going to think about their subject. They're not going to think on a continuous spectrum. They're going to think a lot of times on a categorical scale, and they're going to have like cutoffs in their mind, even when it's continuous, to make it categorical. A common occurrence after presenting an informative visualization is for your stakeholders to ask for the data. All right, so a good idea during a project is to compute the summary statistics for your visualization, use geom call or geom bar with stat equals identity to create the visualization and save the summary data. All right, why do I do this? Sometimes the data changes between creating a visual and sharing it out. The data maybe it's updated and now it's a different visualization. I've had that experience. Additional data might be found after I shared this out. Project scope could change. Maybe we eliminate some cases that I learned, oh, well, really we want to improve the project and get rid of this. Or maybe the data set is completely removed from the database. I've had all of these happen to me. This can cause problems. You have somebody who is high up in your organization that wants data, and you cannot obtain the data that matches the visualization you shared out. You're gonna have to be ready to explain what's going on. It's a bad situation to be in. I save the data frame. I literally hand it out. Boom, I've got it. I'm not at risk. So when your data changes, your visualization can say one story, but then the shared data might say another. If they catch it, that's going to undermine your credibility. Now, something that you can do if you save the original visualization as an R object. Another option is to use ggplot build to extract the computed summary data from geom bar. But this output is going to require an additional step. Also, you have to save the visualization as an R object. This won't work if it's a PNG or a JPEG. Also, if I have to rebuild the bar plot and that data has changed, like, let's say I'm pulling from a SQL database, it might be that I can't get the original data. All right, so now let's talk about time series with line and path plots. Line and path plots are typically used for time series data. Line plots join the data from left to right, while path plots join them in the order that they appear in the data set. So line plots, left to right, path plots, in the order that they appear in. A line plot is a path plot with the data sorted by the x-coordinates. Line plots usually have time on the x-axis, showing how a single variable has changed over time. Path plots show how two variables have simultaneously changed over time, with time encoded in the way the observations are connected. Because the year variable in the miles per gallon data set only has two values, we'll show some time series plots using the economics data set, which contains economics data on US measures over the last 40 years. The figure below shows two plots of unemployment over time, both produced using geom line. The first shows the unemployment rate, while the second shows the median number of weeks unemployed. We can already see some differences in the two variables, particularly in the last peak, where the unemployment percentage is lower than it was in the preceding peaks, but the length of unemployment is high. All right, so we're going to use the economics data set, which is in the ggplot2 package. I'm going to convert the date to the year. I'm going to use that on an upcoming plot, not the first one. And now let's go ahead and have date, time on the x-axis, and let's have unemployment divided by population, the ratio, as the y-coordinate, and let's look at a line. So we can see what's going on, the number of unemployed per population. And so when it peaks, we have a higher unemployment rate. All right, so now let's take the same plot, but now we have a different unemployment metric, and notice this huge spike right here that corresponds to this spike. Huh, that is interesting. 2010 is where I graduated. Look at the job market I went into. All right, so now let's draw both time series on the same plot. All right, so now what we want to do is I want to take the y-coordinate here, the y-coordinate here, take the y-coordinate here, take the y-coordinate here. For each point in time, I'm going to grab the y-coordinate for each of those plots. But now one of those is going to become the x-coordinate, and the other one's going to become the y-coordinate of the upcoming plot. And I could do a scatter plot on this, but I'm going to take it a step further. I'm going to draw a line connecting the dots sequentially by the date that we had. So we could draw a scatter plot of unemployment rate versus length of unemployment. But then we can no longer see the time aspect. So we're going to join the points adjacent in time with line segments, forming a path plot. Before we plot unemployment rate versus length of unemployment and join the individual observations with a path, because of the many line crossings, the direction in which time flows isn't easy to see in the first plot. In the second plot, we're going to color the points to make it easier to see the direction of time. All right, so let's go ahead and look. All right, so I look at here and I can see that there is like a flow of the dots because of how we played connect the dots. And we can go through. Now, I don't know, is this the beginning of the data or the end of the data? I'm pretty sure the other end is over here, but I don't know which one's which. So let's go ahead and add year to the color. Now, in this one, I've got year as a continuous variable. I could have converted this over to categorical and had discrete values. I actually would have preferred that if I was doing this professionally, but I'm just leaving it the way the textbook authors are. So I know that dark is the beginning of the data, light is the end of the data. So I know the data starts here and ends here. And I can kind of, trace out what happens. So, it goes out, goes along, comes out here, then it comes back, then it goes over here, moves around a bit, another year happens, and then it starts moving around, and then it comes over here. We can see that unemployment rate and length of unemployment are highly correlated, but in recent years, the length of unemployment has been increasing relative to the unemployment rate. All right, so to further see this, and this is not in the textbook, I'm going to go ahead and slap on a linear model on top of it to go with each year like this. All right, so now it's much easier for me to see the individual years like that, and you can see the relative slope changes over time like that. With longitudinal data, you often want to display multiple time series on each plot, each series representing one individual. To do this, you need to map the group aesthetic to a variable encoding the group membership of each observation. All right, so now let's talk about modifying the axes. We can use xlab and ylab to modify the x and y axes. All right, and we can remove it altogether with null. All right, so let's look at the default. Notice I don't have xlab, I don't have ylab. I have the default value. So I've got city miles per gallon, highway miles per gallon. But is that clear to my readers? Do they immediately know? No, they don't. And I've got overplotting. And so when I see a darker point, I know that I have, more dots there. And there's going to be 3 different shades. Lightest for 1 dot, in the middle for 2, and then black for 3. Boom, we got this. All right, so now let's say, you know what? I really want to improve that X label. I want to improve that Y label so it's easier for my readers to know what they're looking at. City miles per hour, miles per gallon, highway miles per gallon. Boom, we got it. Now let's say I just want to remove the label altogether. Just put in null and notice that it disappears. This is a good choice when I've got a lot of things going on. I don't have a lot of real estate. I could remove that because this does take up a little bit of section of the plotting area. If I could trim it out, it might improve the visualization. All right, well, that's the labels of the axes. What about controlling the minimum and maximums of the axes? Well, I can use the limit arguments to control the limit of the x axis and the limit of the y axis. Now, these are not limits in the calculus sense. These are limits as in boundaries. The default limit of the boundaries are determined by the data. For continuous scales, use NA to set one limit. So let's say that I want, 5 or greater. I could put the infinite side equal to NA. All right, so let's go ahead and take a look at the scatter plot of drivetrain and highway miles per gallon. Use a jitter plot. Now let's say that I'm only interested in front wheel drive and rear wheel drive, and I'm only, so when I do that, notice that the plot only goes from 20 to 30. So I can also limit the y coordinates, or it only goes up to 30. And let's say I'm only interested in these guys here. Boom, I can zoom in on my data. So I can, tune my visualization to the story I'm trying to tell my stakeholders. Now, let's say that I want the Y axis to go from the minimum value up to 30 to go no higher than 30. All right, well, I put in NA for the minimum. That just says, hey, use the data to figure out the minimum of the Y coordinate. Changing the axes limit sets values outside of the range to NA. You can suppress the associated warning with na.rm equals true, but be careful. If your plot calculates a summary statistic, such as sample mean, this conversion to NA occurs before the summary statistic is computed and may lead to undesirable results in some situations. All right, most of the time, you create a plot object and immediately plot it. But you can also save a plot to be an object in R that is a variable in the R workspace and manipulate that object later. So here, I'm saving the plot that I want to have down the road as P. Once I have a plot object, there are a few things I can do with it. First of all, I can render it with the print function. I find it funny that it's print, not plot, because I mess this one up at work, by the way. But it's print. This happens automatically when running interactively, but in some situations, depending on the system that I'm working on and my interface, maybe no visualization would happen if I just put P by itself as a command. So I need print. I need to say print explicitly. Now, if I want to explicitly have a loop or a function, I should use the print function. So boom, I can use the print function to look at the visualization. Here we're coloring by the cylinders as a discrete data column. We can also save it as an image. So here I'm saving as a PNG. ggSave automatically interprets this aspect of the file name, the suffix, to figure out what type of object you're going to have. And I can control the height and width of the PNG file. It will look different than what's on your screen, so definitely take a look. We can also save it as an R object. This can be convenient when building a plot is slow, when we want to reuse the exact same plot across documents, or you want to postpone rerunning expensive data preparation while iterating on surrounding narrative. Save RDS stores a complete copy of the ggplot object, the data, the mapping, the layers, the settings. So reloading it lets you reproduce the same object without re-executing the code and creating it. So here I can save a plot as an RDS object. So here I'm saving the plot as an R object, not an image. This saves the plot as an image, as a PNG file. This saves it as an R object. And then I can use read RDS to be able to pull in the plot after I've made it. We can also summarize the visualization. And this isn't really important for us. I can use ggplot build to extract the under the hood aspects of the data that went into the visualization. And I can also extract individual components with other functions that we have here. So like layer scales and layer grob. All right, it's been a long video, but this is really good stuff, really important. I really hope, really hope, that's a lot of reallys, that you found this video helpful. I hope you enjoyed it. So remember, life is short, do math.